I am Aiden, and this is the project on asteroid orbit determination. Some background information. An asteroid is a type of minor planet that orbits in the inner solar system. There are a bunch of different types of asteroids, but the ones that are most important to know the orbits of are near-Earth asteroids, whose orbit takes them within 1.3 astronomical units of the sun. And then, more importantly, the potentially hazardous asteroids, which get within 0.05 AU of the Earth's orbit and are more than 140 meters across. These get close enough to do damage and can deal real damage. A little more, every day about 50 tons of stuff are hitting the Earth. Most of it's about the size of a grain of sand, so it just burns up in the atmosphere. Car-sized objects will hit about once a year, but they only might make it down because they are about the minimum size to make it down. Just about 5 meters will make it down some of the time, but rarely. An object the size of the football field crosses orbits with Earth about once every 2,000 years. It's not going to hit every time, though, which is nice. And if we know the orbits of these objects, we can predict with very great accuracy where it will be, when it will be there, and combining that with our knowledge of the Earth's orbit allows for very accurate detection of an object is on collision course with Earth. So the idea here is we take pictures of the same spot in the sky, and we find something that moves, which is going to be an asteroid because the stars do not move at a pace that would be noticeable by any telescope over this period of time. Figure out the orbit of whatever that thing is using multiple observations. In this case, it's going to be asteroids. And these observations will eventually give us the object's velocity and position at a given time, which is enough to fix the angular momentum and energy of the object. And that is all you need in order to fix the orbit. We need 3 variables for position, 3 for velocity, 1 x, 1 y, and 1 z variable for each. We get 1 independent variable per one from right ascension per image and 1 from declination per image. We get 2 independent variables per image. We need a total of 6, so that's a minimum of 3 images. And once we have the orbit, we can find out, does this thing pose a danger to Earth or no? So if we can do that for the entire sky, and the end game is if we can do this with the entire sky, it also might not take long. You think, again, we need like 3 nights to do a certain patch of sky, which is not too long. We can know what objects are going to hit us and when, assuming we don't do anything, and then we know what we need to do by when. So the plan for the summer project was to use the gamma ray optical robotic telescope to image fields where particular asteroids should be, and then helpfully enough, GORT will both use digital star catalogs to determine what the stars in the image are and plate solve the image as well. And then all we have to do is find the asteroid, and the plate solved image will have the celestial coordinates. If we track these coordinates over multiple nights, we can use them to find the orbit of the asteroid. So for calculating the orbit, we used FindOrb, which is a software that is on the website of Project Pluto. So thanks to them for letting people use the software. Data had to be input in this format. It's from the days of punch cards, so that's not fun. In order, what this is, it's a designation of what object you're talking about, so you know, and then year, month, day, and hours, minutes, and seconds in a fractional day, and then you have the right ascension and declination in hours or degrees, and then minutes, seconds, and fractional seconds. This U54 at the end here is an observatory code, so you can tell the software where exactly the image is from. For the results we got, we were able to get some images. We predicted the orbits for 2 asteroids, and below we have diagrams of the predicted orbits and numbers that describe those predicted orbits. This diagram belongs to the predicted orbit of the asteroid known as Ziegina. The semi-major axis predicted here is take what's the closest approach and what's the furthest approach from the body it's orbiting. You take the average of that, and that's semi-major axis. It's a good one number thing to get an idea of the size of the orbit. We got about 2.873 astronomical units, plus or minus about 5 thousandths. The eccentricity is how much like a circle it is, and 0 is a perfect circle. And as you go up, the orbit gets less than a circle. We got 0.194, or a little more or less than that. The inclination is just how tilted the orbit is relative to the plane of the rest of the solar system. Where we got about 18.5 degrees here. The longitude of the ascending node is counterclockwise, assuming you are north in the solar system of space, and you're looking like that. The longitude of the ascending node would be the ascending node is the point where it goes from below, the object crosses from below the object to above it, and so the ascent, and you count that longitude in degrees counterclockwise from the first point in Aries. And we got about 171 degrees for that. For the periapsis argument, we got about 203 degrees. The periapsis is just a point of closest approach to whatever it is orbiting. And so this is about 203 degrees, again, counterclockwise, north in space of the plane of the solar system. that far from the ascending node, to about 230 degrees. And the next time of periapsis passage we got was 2:11 a.m. April 30th, 2025 terrestrial time, plus or minus about 1.3 days. Terrestrial time and universal time are basically the same thing, but terrestrial time does not count leap seconds like universal time does. And we got a second orbit. It belongs to the asteroid known as Electra, this prediction. We got semi-major X about 2.45 AU, eccentricity about 0.036, and inclination of about 20.34 degrees, the longitude of the ascending node about 149 degrees, periapsis argument about 322 and 3/4 degrees, and a time of periapsis of 3:38 and 28 seconds p.m. July 12th, 2026 terrestrial time. So with these the uncertainties, by the way, were not given from the orbit software, so I was not able to give those there. So the actual orbits, we got the actual orbits as well, and compare that to their to predict orbits. We were off by about 25 thousandths on the semi-major axis and eccentricity for Siegina, about 2 degrees of inclination, and about 18 degrees of periapsis argument. For Electra, it was a little worse. Off by about 0.65 in AU, about 0.17 eccentricity, again about 2 degrees of inclination, and about 85 degrees of periapsis argument. So most of the time they're reasonably close, but not actually all that accurate. It's not surprising. We had a very limited number of observations that we could use. So the conclusions, this is not easy. A lot can and will go wrong. We had a lot of problems involving weather, be that fog, rain, whatever, and then also just sometimes the telescope didn't work and give good images. But in the end, more observations lead to more accurately predicted orbits. So what we tried, it did work, but with the limited data, results could have been better. Next for this field is the currently under construction Vera Rubin Observatory, with what will be the largest digital camera ever constructed. It should be able to survey the entire portion of sky visible to it in just 3 days. That's just one of the reasons it's going to wind up better than what we did here. One of its advantages is that large field of view. Another one is that it's located at the edge of the Atacama Desert, so it's not going to get as much cloud cover or rain, so it's going to be able to take more images. And then also it's a professional telescope with a bunch of people who this is their full-time job. As for what's next for me, I'm going to take this big experience of things going, just basically nothing going right the first time, and apply that to my life going forward. I'm really going to try to stay somewhat in this NASA-related area. Hopefully I'm able to. And more immediately, my senior year of high school starts on Monday. I also want to thank Kevin and the entire N3 program for giving me this opportunity, and Kevin for helping me at this point. And I was wondering if anybody had any questions for me.